FPGAs make it possible to have custom-designed high-density hardware in an electronic circuit, with the added bonus of having the possibility of changing it whenever there is the need, even while the whole application is still running. Nowadays, different languages can be used to describe the functionality that has to be implemented on the device. Once the functionality has been described, we can then use the design software of the device manufacturer to translate it into a configuration file for the device that can be downloaded on the FPGA. The flexibility of having custom adaptable hardware in an application is the factor that has determined the popularity of FPGA devices in a broad range of fields. If the FPGA is paired with a general-purpose processor, as an example, the most demanding sections of the software can be translated into hardware cores that accelerate program execution, yielding notable speed-ups in the overall execution. This is the case, and as an example, when software section executed serially on the processor can be translated into hardware that can exploit the parallelism of the algorithm. Configuring an FPGA means changing its functionality to support a new application, and it is equal of having some new piece of hardware mapped on the FPGA chip, having it to implement the new functionality. Considering the fact that an FPGA can be programmed an unlimited number of times, it may be better to use reconfiguring an FPGA rather than configuring it. Within this context, an FPGA makes it possible to have custom-designed high-density hardware in an electronic circuit, with the added bonus of having the possibility of changing it whenever there is the need, even while the whole application is still running. As we all know, the free food was yesterday, and the versatility and programmability of a programmable gate array comes at a cost. Only a few years ago, the algorithms that could be implemented in a single FPGA chip were fairly small. At the beginning of the century, as an example, the largest FPGA could be programmed for a circuit of about 15,000 logic gates at most. Now, to give you an idea of how much 15,000 logic gates are, think that a fast 32-bit adder requires a couple of hundred gates. Therefore, you can easily see that the capabilities of such devices were somewhat restricted. More recently, though, FPGAs have reached a size where it is possible to implement more than a reasonable portion of an application in a single FPGA. Well, not only portion, but in some cases the entire application itself. Moreover, nowadays we can find FPGAs in the cloud, like in the Amazon F1 instances, and this is exactly the kind of system we are going to target during our classes. In the simplest scenario, which can be termed compile time reconfiguration, CTR, the configuration of the FPGA is loaded at the end of the design phase, and it remains the same throughout the whole time the application is running. In order to change the configuration, one has to stop the computation, reconfigure the chip, resetting it, and then start a new application. Compile time reconfiguration was for some years the only kind of reconfiguration available for FPGAs. With the evolution of technology, though, it becomes possible to considerably reduce the time needed for the chip reconfiguration. This made it possible to reconfigure the FPGA between different stages of its computation, since the induced time overhead could be considered acceptable. This process is called runtime reconfiguration, RTR, and the FPGA is said to be dynamically reconfigurable. Runtime reconfiguration can be exploited by creating what can be considered as a virtual hardware, in analogy with the concept of virtual memory in general computers. A further improvement in FPGA technology allows modern boards to reconfigure only some of the logic gates, leaving the other ones unchanged. This partial reconfiguration is of course much faster in case only a small part of the FPGA logic needs to be changed. When both these features are available, the FPGA is referred to be partially dynamically reconfigurable.